Okay, let's dive into this. Welcome to today's Explainer, where we're going to unpack a piece of tech that literally sounds like it was pulled straight out of a sci-fi novel but is very quickly becoming our reality. Today, we're looking at ultra-fast, low-power edge intelligence. Specifically, we're focusing on something called Photonic Neuromorphic AI. If you've ever wondered where the absolute cutting-edge future of computing hardware is heading, well, you are in exactly the right place. We got to start our journey today with a super practical challenge that engineers are wrestling with across the globe right now. Basically, what happens when AI gets too hot to handle? I mean, if you've been following the massive explosion in artificial intelligence lately, you already know these AI models are scaling up incredibly fast. But here's the catch: they're hitting real-world physical limits. Traditional GPUs are rapidly approaching data center power limits and silicon thermal ceilings, just trying to keep pace with the massive computational demands we're throwing at them. They are literally burning up.
So, to break this all down, we'll start with the GPU thermal wall. Explore computing AI with light, take a look inside Imagenta's photonic engine, see how we're smashing the bottleneck, and finally, look at the future of edge AI.
Let's kick things off with Section 1, the GPU thermal wall, and hitting those physical limits.
Look, we are at a really critical juncture here. Traditional electronic AI hardware suffers from severe high-power consumption and thermal bottlenecks. Like we just mentioned, traditional GPUs are hitting a massive wall as these models scale up. They demand huge, honestly sometimes unsustainable amounts of electricity to run. And as a direct consequence, all of that electrical resistance creates a tremendous amount of heat. You just can't keep stacking processors on top of each other without eventually hitting an insurmountable thermal ceiling, right? It's basic physics. Now, what's really interesting about this is that the root of all this trouble is something called the von Neumann bottleneck. This is the critical performance limitation in traditional architectures, where the whole system is essentially choked by data constantly having to move back and forth between the memory and the processing units. It's like a never-ending digital traffic jam. And I want to stress this point. This isn't some temporary software bug that a quick patch is going to fix. No way. This is a fundamental architectural flaw in the very way conventional electronics are built. The commute for the data just takes way too much time and burns way too much energy. So how on earth do we solve a physical hardware problem of this magnitude?
Well, that brings us to Section 2, computing AI with light. A true paradigm shift.
When you actually compare the old electronic von Neumann architecture to this new photonic neuromorphic approach, the contrast is absolutely wild. On one hand, you've got the old standard, high power, slower processing because of that data commute we just talked about, and severe thermal bottlenecks. But on the other hand, the photonic neuromorphic approach offers minimal energy use, sub-nanosecond speeds, and barely any thermal footprint at all. We are quite literally transitioning from a heavy, hot electronic past to an ultra-efficient, light-driven future. It's brilliant.
Let's get into the nitty-gritty in Section 3, inside Imagenta's photonic engine.
Okay, so here's how this groundbreaking TFLN-based suite actually operates. Step 1. Data enters ultra-low-loss optical waveguides. Next, in Step 2, electro-optic microring resonators modulate the signal, essentially acting as artificial synapses. And finally, Step 3. Localized matrix vector multiplication is performed entirely in the optical domain. And this brilliantly illustrates the real magic here, that artificial synapses concept. The Imagenta photonic engine uses these microring resonators to mimic the exact way the human brain processes information. It enables this crazy brain-inspired processing, and it performs incredibly complex math right there in the photonic domain using nothing but light. How cool is that?
Moving right along to Section 4, smashing the bottleneck and unlocking unprecedented speed.
Sub-nanosecond. I'm going to say that again. Sub-nanosecond latencies. So, the crucial point is, by utilizing light instead of electrons, the processing speed becomes almost entirely instantaneous. You are operating literally at the speed of light, completely bypassing those terrible traffic jams of traditional computer memory banks. This sheer speed is what allows the system to absolutely smash that traditional bottleneck to pieces.
But you know what? Speed isn't even the only benefit here. By computing directly in the optical domain, the architecture maintains a minimal thermal footprint. Because it bypasses that pesky von Neumann bottleneck entirely, it delivers those incredible sub-nanosecond speeds while drastically cutting down on energy consumption. We're talking about generating just a tiny fraction of the heat of a standard GPU. So think about it. You get vastly more speed for a fraction of the power with almost zero heat. It's a total game changer.
Let's move to Section 5 and see how this builds into the future of edge AI and its real-world impact.
Make no mistake,
Photonic engines are completely revolutionizing edge AI applications across the board. We're talking about power-constrained drones, advanced robotics, and high-speed real-time systems. Because true edge intelligence, it absolutely requires maximum power efficiency and zero lag. If you've got a drone navigating a super complex environment or an advanced robot performing a highly delicate task, it simply cannot wait for data to travel all the way to a cloud server and back. It needs to think locally, it needs to think efficiently, and it needs to think instantly. This architecture is what makes that elusive level of efficient edge AI an actual reality.
Which leaves us with this final, super vital question to ponder today. What breakthroughs will we achieve when our edge devices can finally think at the speed of light? Photonic neuromorphic computing isn't just some small incremental step forward. It is a massive leap completely beyond conventional AI hardware limits. It redefines what our machines are capable of doing out there in the real world. Just think about the sheer possibilities that opens up. Wow. Anyway, thank you so much for joining me for this explainer. Keep exploring, keep learning, and I'll catch you on the next one.